Welcome to our presentation on shortcutting fast failover routes in the data plane. My name is Klaus Tüchel-Förster, and this is joint work with Abhoff Schukla. So today we heavily rely on the internet and networks and overall. For example, for your private use when you have smartphones, laptops, or when you do online shopping or in your smart home, but also in more industrial contexts such as smart grids and in data centers, and they all rely on the underlying network to function. However, network failures are rather not the exception anymore, but it feels like they are the norm. Maybe you remember the recent Facebook outage, which took quite some time to resolve, but these network errors, they also happen to other big companies such as Google or also major ISPs such as Verizon. And even though these network outages usually get somewhat quickly resolved, they still violate service level objectives and agreements. For example, the famous 5 nines of high availability, but also objectives such as high throughput, low latency, and minimal packet loss and jitter. And even though there are many causes for network failures to happen, in this talk we want to focus on link failures. In the case of link failures, there's usually some sort of fast reroute mechanisms implemented in modern networks, which then help to restore network connectivity quickly. For example, to use disjoint trees or routing structures as proposed by, for example, Chiesa et al., but also methods such as U-turn, alternates, or IP fast reroute. Here the idea is that we restore network connectivity quickly at the cost of possibly having some detours and transient loops, and also disturbing other traffic while causing packet loss. So even though these fast reroute mechanisms impact performance, they maintain the high goal of reachability until slower network convergence kicks in. And generally, control plane convergence in this context is quite slow, and hence data plane convergence mechanisms have been developed that are much faster, but they are not always fast. For example, DDC uses link reversal, which can be quite good in practice, but in the worst case, the runtime can be quadratic in the size of the network, and there's no way around it when using link reversal protocols. And hence, we would like to introduce shortcut to mitigate some of these problems. So the general idea of shortcut is that it enhances fast reroute mechanisms to route in a loop-free fashion, avoiding costly detours, and decreases link load by leveraging data plane programmability. So this is a teaser. Now let's go a bit more formal and get some design overview. So the problem statement that we consider is that local fast reroute mechanisms maintain reachability under link failures, but incur extra detours and load. So our goal is, how can we locally and rapidly remove inefficient route detours before the slow convergence kicks in? To this end, let me give you a small motivational example. On the left side, we have a network with 4 routers and 3 hosts, and we have 2 flows. A black one going from S via S1, S2, S4 to D, and a blue one going from H to S using S2 and S1. In all these routers, we have some routing tables installed, and here we zoom in on the one installed as S1. It has one entry for the black flow, namely if the packets come from S and go to D, then we send them to S2, and for the blue flow, when they come from S2 and go to S, then we send them to S. Now, if we introduce a link failure, like here between S2 and S4, then without changing anything, packets will just be lost, and hence we introduce some fast reroute mechanisms. Here the idea is that then the black flow gets turned back to S1, and we now color it red to make it easier to see. For the fast reroute mechanism, we also extended the routing table for the node S1, where we now see the routing entry for the red rerouted flow in red, but this is just a visual aid. Because all this router does is that it matches that the packets go to D, that they come from S2 and they go to S3, and hence we avoided this failure and maintained reachability. However, there's still the issue that now we have this extra unnecessary loop between S1 and S2, and that the rerouted flow also disturbs the blue flow because it shares now the capacity on this link, and for example, they might both lose half of their throughput. And this is then where our proposal shortcut comes in. The idea is that that the router S1, you can observe that now the flow gets routed through a non-standard lower priority output, namely to S3, and hence we no longer need to forward to S2, but can rather shortcut this rule and directly route to S3, hence improving network performance. So let me give you a small overview of the solution design of shortcut. So the idea is that shortcut sits between fast reroute mechanisms and data or control plane convergence and kicks in directly after fast reroute kicks in. It can be implemented purely in the data plane, and it is not a fast reroute mechanism on its own, but rather augments fast reroute solutions. In that sense, it also has the benefit that it's mostly agnostic to fast reroute mechanisms because it just shortcuts routes and is not interested in how the fast reroute mechanisms actually works. Moreover, it can be implemented purely locally on the routers and switches. We don't need any communication between router, switches, and controller. And even though we, of course, need to install it ahead of time, but once it's installed, we don't need any further communication. Moreover, we also don't need to do any probing, meaning we don't create extra traffic and delays. And we also don't need to modify the packets, meaning, for example, we don't disturb network functions. Moreover, the routers also don't need to remember packets, meaning we don't need extra memories in the routers. And the key insight for shortcut to work is that if we detour along a loop, then we will visit a router or switch more than once, and hence we can infer loops from the traffic and we can shortcut them, as here in our earlier motivational example, that if traffic at S1 now is also going to S3, even though to S2 would be the standard output, that then we can shortcut the routes and directly reroute to S3 without having any extra detours. So let us now look at some formal assumptions that we need for shortcut to work. So first we assume a standard that the network is a directed graph and that when we have flows, they are routed from some source to some destination, deterministically along a simple path before failures. Moreover, we assume that the forwarding matches on some header fields such as source and destination, but also on the incoming port and on incident failures, because we don't want to route on a failed link. Moreover, we assume that the fast reroute mechanisms are implemented statically ahead of time, so with the properties as above, but of course that now the route no longer needs to be a simple path, but can be a walk, because these are the loops that we want to shortcut. Moreover, we assume that each node has an ordered priority of outputs for each flow, where each input can still have a different list of outputs, but that still for each flow, for each node, there's a global ordering of the priority of the outputs. And we will see some examples soon. Then the shortcut mechanism is quite simple. If fast reroute routes the flow via lower priority output, then these higher priority outputs can be removed because they will eventually converge into the lower output anyway after some loop. Let me give you a high-level intuition of this idea. From the bottom left, we have a router where before failures the flow gets routed along the red path. First comes from the left, exits to the top. And then later, if there's some failure, it will visit the node again, here from the bottom in blue, and exits to the right in blue as well. Now this blue output is a lower priority output because it only kicks in after some failures happen, and hence we can remove the top output in red and just converge it to the blue output on the right. Now we see the result on the bottom right, namely that now the red packets are also coming from left to right, meaning we no longer have some temporary loop in the network, but can rather shortcut our routing. Let me give you an example where we can apply this scheme in some context. So earlier in this session, we had to talk about tree, which uses edge, disjoint path, and trees to route packets after failures. So in this example, we have two paths, the purple and the blue one, and we first try the purple one, and if we hit a failure, here shown with the black X, then we route back to the source and try the blue path. With shortcut, we can directly shortcut these routes, meaning we no longer need to use the purple path and can directly fall back to the blue path, and also in general for any edge disjoint path fast reroute mechanism. We can apply this idea analogously for arc disjoint spanning arborescences, for example, proposed by El-Hourani et al. And Chiesa et al. So here we have different routing trees, which are also disjoint. For example, here red, blue, yellow, and green one. And there might be a rule, for example, that we first use the red tree, then the blue tree, then the yellow, and then the green tree. And with shortcut, we can then directly shortcut some local loops inside these networks after failures. So the main formal properties that we then derive for shortcut are first, that it can be implemented purely locally and is non-intrusive. We don't need messages between nodes or to the controller. We also don't need to change the packets. We don't need to have memory at the routers. And we can have a fast reaction because shortcut is then triggered within one end relay after the failures kick in. Moreover, we then also have the main property of shortcut, that namely if the fast rerouting succeeds, that then shortcut can improve it. So that if fast reroute maintains reachability, that then shortcut also maintains reachability and removes routing loops for a single link failure, where we show the formal proof in the paper. We also performed a proof of concept evaluation, where we took 4 P4 switches in Mininet, as shown on the bottom left, and routed the flow, shown in solid blue, from the source via S1 to S2 to S4. We then introduced a failure between S2 and S4 in a controller script where we failed this link and then ordered the node S1 to, instead of route to S2, to rather route to S3. And then we plot the performance of our experiments in the bottom right plot, where in red we see the performance of shortcut, where on the y-axis we have the throughput and on the x-axis we have the time. So you can see the red shortcut plot quickly goes back up in throughput, whereas the dotted blue control plane convergence plot takes some time to recover, because it first needs to recompute the global routing and roll it back out, whereas shortcut can directly shortcut these failover routes. Still, shortcut has some limitations, and hence we see different future work opportunities. For example, if we have temporary failures or link flaps, then shortcut does not switch back automatically, and here it might be interesting to consider some delays in probing mechanisms. Moreover, it would also be interesting to study the interplay with non-static fast reroute mechanisms, for example, data plane convergence methods, but also header changes such as in MPLS and segment routing. Moreover, we believe it would be easy to extend shortcut to multiple failures, but also to routing along multiple paths and things such as packet duplication fast reroute mechanisms. Moreover, it would be interesting to implement shortcut in a hardware P4 switch, as currently it's just a proof of concept, which nonetheless showed the performance benefits. In conclusion, shortcut augments fast reroute mechanisms to route in a loop-free fashion, avoiding costly detours, and decreases link load by leveraging data plane programmability. It's purely local, non-intrusive, and has fast reactions. So we don't need messages to other nodes, there's no packet changes, we don't need memory at the routers, and it's triggered within one end-to-end delay after the fast reroute mechanism kicks in. Moreover, the main theoretical property is that if the fast reroute mechanism succeeds, then shortcut can improve it, because then it maintains reachability and removes routing loops for a single link failure. Thank you very much for your attention.